Welcome to Robotics Next Lecture, technically Lecture 12. This is your Professor Atif Fareed Muhammad. We will be looking at non-linear control of manipulators, non-linear and time-varying systems, the control problem for manipulators, the practical consideration, how to resolve. We'll discuss some scenarios on that. Cartesian-based control systems and adaptive control. Now let's look into non-linear control of manipulators with an example. Non-linear control of manipulators is a critical area of study in the field of robotics, particularly when dealing with the systems that exhibit complex nonlinear dynamics. Unlike linear control systems, which assume a proportional relationship between input and output, nonlinear control systems are designed to handle the inherent complexities and uncertainties present in the real-world applications. These complexities often arise from factors such as friction, backlash, and varying payloads, which can significantly affect the performance and stability of a robotic manipulator. Advanced control techniques such as feedback linearization, sliding mode control, and adaptive control are employed to ensure the precise and stable operation of these systems. These methods enable robotic manipulators to perform tasks with high accuracy and reliability, even in the presence of disturbances and uncertainties. One prominent example of non-linear control of manipulators in healthcare is the use of robotic arms in surgical procedures. Surgical robots, such as Da Vinci surgical system, rely on sophisticated control algorithms to assist surgeons in performing minimally invasive surgeries with advanced precision and dexterity. The nonlinear dynamics of these robotic arms, which include factors such as joint flexibility and varying tissue interactions, require advanced control strategies to ensure accurate and stable movements. Feedback linearization techniques, for instance, can be used to transform the nonlinear dynamics of the robotic arm into a linear system, permitting for more straightforward control, design, and implementation. This enables the robotic arm to follow the surgeon's commands precisely, reducing the risk of errors and improving patient outcomes. So, non-linear control example, consider a robotic arm with joint flexibility, maintain position under varying loads. This can be a factory or a manufacturing facility example. Feedback linearization techniques, as I just discussed. And let me continue that example. In addition to the surgical applications, non-linear control of manipulators is also crucial in rehabilitation robotics. Robotic exoskeletons and prosthetic devices designed to assist individuals with mobility impairments often employ non-linear control techniques to adapt to a user's movements and provide the necessary support. For example, an exoskeleton used to gate rehabilitation may utilize adaptive control algorithms to adjust its assistance based on the user's walking pattern and muscle activity. This adaptive capability ensures that this exoskeleton provides the appropriate levels of support, enhancing the user's mobility and facilitating the rehabilitation process. By leveraging nonlinear control techniques, these robotic systems can effectively address the complexities and uncertainties associated with human-robot interaction, ultimately improving the quality of life of the individuals with mobility impairments. The second example is a two-link planar robot. We can deal with this to look at trajectory tracking, sliding mode control. Let's look into this in a little bit more depth. Imagine you have a robot arm with two segments, kind of like your arm, with an upper part of the forearm This robot arm needs to follow a specific path or trajectory, like drawing a circle or moving from point A to point B. The challenge is to make sure that arm follows this path accurately even if there are unexpected changes or disturbances, like someone gently pushing the arm. To handle this, we use something called sliding mode control. Think of it like trying to keep a book sliding straight across the table. If the book starts to veer off course, you quickly adjust your hand to push it back on the right path. Similarly, sliding mode control constantly checks where the robot arm is and makes quick adjustments to keep it on track. It switches between different control actions very rapidly to correct any errors and ensure the arm follows the desired path smoothly. This method is great because it is robust, meaning it can handle unexpected changes or disturbances effectively. Now let's look at nonlinear control example 3, a robot manipulator with uncertain dynamics, robust stability, and Lyapunov based control design. Let's look into this with an example. Imagine you have a robot arm that needs to perform tasks like picking up objects or assembling parts. However, this robot arm has some uncertainties in its dynamics, meaning it might behave slightly differently each time it moves due to factors like wear and tear or varying loads. To ensure the robot arm remains stable and perform its tasks accurately, we use a method called Lyapunov based control design. Think of this control like trying to keep marble at the bottom of a bowl. The bottom of the bowl is the stable point where you want the marble to stay. If you give the marble a small push, it might roll up the side of the bowl, but gravity will pull it back down to the bottom. In the same way, this control design uses a specific and special function called Lyapunov function to ensure that the robot arm always returns to its stable state even if it gets disturbed. This method helps the robot arm handle uncertainties and maintain stability, ensuring it can perform its tasks reliably. Nonlinear and time varying systems. Let's look into this in a little bit more depth. Imagine you have a robot that can fly like a drone. This drone needs to navigate through the air, but the environment around it is always changing. For example, the wind might be calm one moment and gusty the next, pushing the drone off course. These changing conditions make it challenging to control the drone effectively. This is an example of a time varying system, where the factors affecting the drone's movement change over time. To handle these changes, we use spatial control techniques. One such technique is called gain scheduling control. Think of it like adjusting the settings on your bike as you ride. If you are going uphill, you might shift to a lower gear to make paddling easier. Similarly, gain scheduling control adjusts the drone's control settings based on the current conditions like wind speed and direction. This helps the drone stay on course and maintain stability even as the environment around it changes. By using these adaptive techniques, we can ensure that the drone performs well in a variety of situations. Now let's look into another example, an underwater robot with time varying drag. Now think of gain scheduling control like adjusting the sails on a sailboat. When the wind is strong, you pull in the sails a bit to keep the boat steady and on course. When the wind is light, you let out the sails to catch more wind and keep moving. Similarly, gain scheduling control adjusts the drone's control settings based on the current wind conditions as we discussed earlier. If it is windy, the drone might adjust its rotors to work harder to keep it stable. So this is time varying drag, and it also looks into the depth control with the adaptive control techniques. So hope this has been helpful. A robotic system with time varying payload. We look at maintenance performance, maintain performance, and model predictive controlling. Imagine you have a robot that carries different items, and the weight of these items changes all the time. One moment the robot might be carrying a light box, and the next it could be lifting something much heavier. These changes in weight make it tricky for the robot to move smoothly and accurately. This is where model predictive control comes into play. Think of a predictive control like planning your route on a road trip. Before you start driving, you look at a map and plan the best path to take, considering things like traffic and road conditions. As you drive, you keep checking the map and adjusting your route if you encounter unexpected detours or traffic jams. Similarly, model predictive control helps a robot plan its movements ahead of time, considering the current weight it is carrying. It constantly updates this plan as the weight changes, ensuring the robot can move accurately and effectively. No matter what it is carrying, this way the robot can handle varying loads and still perform its tasks effectively. The control problem for manipulators, our first example is a 6 degree of freedom manipulator. We look into precise end effector positioning and computed torque control. Now imagine you have a robotic arm like the ones you might see in a car factory. This arm needs to do very precise tasks like picking up specific part and placing it in exactly the right spot. The challenge is to make sure that the arm moves just right every single time, even if there are little changes or disturbances, like the weight of the part varying slightly or some friction in the arm's joints. To tackle this challenge, we use something called the control problem for manipulators. Think of it like trying to guide a friend through a maze over the phone. You need to give them clear and precise instructions so they do not get lost or bump into walls. Similarly, the control problems involve creating a set of instructions or control algorithms that tell the robotic arm exactly how to move to perform its tasks accurately. These instructions need to account for any uncertainties or changes, ensuring the arm can adapt and still do its job perfectly. This is really important in places like factories where precision and reliability are crucial. Another example is a manipulator with joint friction, the compensation for friction effects, and friction compensation techniques. Let's look into this with an example. Now let's take a robotic arm that can move in 6 different ways, kind of like how your arm can move up and down, left and right, and rotate in different directions. This robotic arm needs to place objects very precisely, like putting a peg into a hole. To do this accurately, the arm needs a smart way to control its movements, and that's where computed torque control comes in. Think of computed torque control like a video game where you have to guide a character through an obstacle course. To succeed, you need to plan each move carefully, considering how fast to run, when to jump, and how to avoid obstacles. Similarly, computed torque control calculates exactly how much force or torque each joint in the robotic arm needs to move just right. It takes into account the arm's current position, speed, and exact path it needs to follow. This way, the robotic arm can make precise movements and places objects accurately. This just like a pro gamer navigating through a tough level. The control problem for manipulator, third example, This is a manipulator with a backlash and gears, minimize positioning errors, and backlash compensation strategies. Now let's look into this with an example. Another example. Now let's have a robotic arm that moves around to do tasks like picking up and placing objects as discussed earlier. Now just like how it is harder to move your arm if you are wearing a tight jacket, the robotic arm can have tough time moving smoothly because of friction in its joints. This friction can make the arm's movements jerky or less precise, which is not good if the robot needs to do detailed work. To fix this, we use something called friction compensation techniques. Think of it like oiling the hinges of a squeaky door. When you oil the hinges, the door swings open and shuts smoothly without any noise. Similarly, friction compensation techniques adjust the robot's arm's movements to account for the friction in its joints. Robot control system adds a little extra force to overcome the friction, making sure that the arms move smoothly and accurately. This way, the robotic arm can perform its tasks more precisely, just like a well-oiled machine. Now, let's look into practical consideration. We'll first look into sensor noise in feedback loops, then we'll go to actuator saturation. With the sensor noise and feedback loops, the issue is degraded performance, and the solution is filtering techniques. Now let's look into some filtering techniques. Filtering techniques are essential tools used to improve the quality of signals or data by reducing noise and unwanted components. One common technique is low-pass filtering, which allows low-frequency signals to pass through while blocking high-frequency noise. For example, if you're listening to a music and a lot of background hissing, a low-pass filter can help reduce the hissing so you can enjoy the music more clearly. Another technique is high-pass filtering, which does the opposite by permitting high-frequency signals to pass through while blocking low-frequency noise. This can be useful in situations like reducing the rumble from traffic in the recording of someone speaking, making the speech clearer. So, other filtering techniques include band pass filtering, which allows signals within a specific frequency range to pass through while blocking others. This is similar to tuning a radio to listen to your favorite station while blocking out other stations and noise. Kalman filtering is another advanced technique that uses a series of measurements over time to produce estimates of unknown variables that are more accurate than those based on single measurement alone. For instance, it can help track the position of a moving car using GPS data more accurately by combining it with information about the car's speed and direction. Lastly, moving average filtering smooths data by averaging a number of points from the input signal, which helps reduce random noise and provides a clearer picture of the overall trend, like smoothing out daily temperature measurements to see the weekly trend more clearly. These techniques are widely used in various applications, from audio processing to scientific research and engineering. The actuator saturation is a scenario where the issue is limited control authority. Solution is anti-wind-up strategies. Now let's look into this with an example. Consider a robotic arm that uses motors to move its joints. Each motor has a maximum torque it can produce. If the control system sends the signal requiring more torque than the motor can provide, the motor will saturate and the arm may not move as intended. To solve this, an anti-wind-up controller can be implemented. This controller monitors the difference between the requested torque and the actual torque produced by the motor. If the motor saturates, the anti-wind-up controller adjusts the control signals to prevent errors from accumulating. This ensures that the robotic arm remains stable and can still perform its tasks accurately, even when the motors are operating in their limits. By using anti-wind-up strategies, control systems can better handle actuator saturation, improving performance and maintainability. The third example would be real-time implementation constraints, the computational delays, and the efficient algorithms and hardware. I suggest you to conduct a little research in this by yourself using Google Scholar or IEEE Explore. Cartesian control systems, a robotic arm performing a pick and place task. We have discussed this in quite detail. However, when applying Cartesian based control systems, the control objective is Cartesian space trajectory following. The approach we use can be inverse, kinematics, and Cartesian control. I suggest you to conduct a little research on this by yourself using Google Scholar or IEEE Explore. Last not the least, adaptive control example, a robot manipulator with unknown payload. We discussed this in quite detail earlier, so I will just go through the slide. The control objectives are adapt to changing dynamics like disturbances or any friction, etc. Approaches adaptive control laws. We have discussed that in quite depth. See you next lecture. Happy learning.